Let's go ahead and continue our discussion of electricity, and we're going to talk about Ohm's law and kind of how that relates to current, resistance, and voltage. And you can kind of see here that was one of the relationships that I said we will end up talking about. And then the last thing that we're going to look at is we're going to talk a little bit about some of the factors that affect resistance. We'll talk also a little bit about electricity and some safety. Now you know that current is going to be these moving charges per unit of time. More charges pass a point, we have more current. Less charges pass a point in that same given amount of time, less current that we have. If I have a bigger power source, 9-volt battery say versus a small 1.5 AA, you can push more charges along. And if you push more charges along, then what you do is you have a larger current. So we can say that voltage and current are going to be directly related to one another. But voltage isn't the only thing that's going to affect current. The other thing that's going to affect current is going to be resistance. Now, resistance, it's basically what I'd like you to think of as friction of electricity. As these particles are moving through the wire, they're constantly bumping into one another. That's maybe why sometimes you'll notice that wires do become warm because of this resistance and those particles moving through it. But in electricity, this electrical friction is called resistance. Resistance, it basically says, according to the definition, it is the impeding movement of charge through a material. And it's going to be measured in ohms. Symbol omega, kind of like a horseshoe a little bit there, upside down. George Ohm, that unit ohms was basically named in honor of him because he wanted to see how resistance, voltage, and current were going to be related to one another. He studied that relationship between these three variables, and really what he found out was the resistance that is in a material, whether we talk about a copper wire, a motor, things like that, was going to be constant across a wide range of voltages. Now, we're not talking about the low extremes or the very high extremes, but if we talk about a large middle portion of it, he found out that the resistance of that material was constant. So he was able to conclude that voltage was going to be equal to the current multiplied by the resistance. So voltage is V, measured in volts, current is I, measured in amps, and resistance R, and as we said, it's going to be measured in ohms. When looking at materials, it was found that resistance was going to depend on 4 factors. Now, I said it was constant across a wide range of voltages, okay, but itself, when we look at just resistance itself, there's going to be 4 factors that it depends on. The first one is going to be the length of the material. Think of this, if I have a short wire, again, going from point A to B, there's going to be, a short distance. But if I increase that distance for A and B, there's more interactions between the particles, thus causing more resistance. So as it says here, shorter materials, less resistance. Longer materials or longer wires are going to give you more resistance, and the reason being is because you're going to have more interactions between the particles, more of them bumping into one another, going from point A to point B. Second one's going to be cross-sectional area. What I basically say is this is the diameter of the material. If you want, you can say the diameter of the wire. Think of this, if I have a tank of water and I'm trying to get it through a tube that's only about as big as or big around as my pencil, it's going to take a long time to drain that tank. But if I have a huge PVC pipe, I can fit more water through that PVC pipe, thus draining that tank a lot sooner. Okay, so bigger cross-sectional areas, less resistance. Smaller cross-sectional areas, more resistance. And this is what I was saying down here. Think of this as the ability to move a volume of liquid. Bigger tubes allow more material to flow, and if you have more material to flow, you're going to accomplish the job sooner. Third one's going to be temperature. Okay, As we increase the temperature, this goes back to chemistry, but if you increase the temperature, those particles that are moving around now, they start bumping into one another a lot more. So higher temperatures give you more resistance. Lower temperature, those particles start to slow down. And if they slow down, they're bumping into each other less. And if they're bumping into each other less, you have then less resistance. And the fourth one simply is the type of material. Okay, we know that metals are going to be good conductors, but different metals have different resistances. Okay, we use copper. It's cheap, but it's not the best resistor. Okay, it'll have more resistance than say gold or silver, but gold and silver are going to be too expensive to use. So different types of materials also have different resistances. Let's go ahead and talk about superconductors. We talked about resistance and things like that. If we lower the temperature, fewer collisions take place, thus lowering that resistance. But it was found that if we lower the temperature of some materials enough, get them cold enough, okay, there will be absolutely no collisions at all. So if there's no collisions, that means that there's no friction. Okay, and these materials are going to be called superconductors. It's just any material that has no electrical resistance at or below a certain critical temperature. As we said, superconductors have no electrical resistance at or below a certain critical temperature. If it's found that, say, a material becomes a superconductor at -250 and those particles stop moving, what you'll also find out then is at -255 degrees Celsius, it is still going to be a superconductor. So at or below that critical temperature is when it becomes that superconductor. Table 19.3 in your book will show some materials that are going to be superconductors and also the temperature at which they become those superconductors. Although we said copper is a great conductor, there will be some materials that are better, but it's at that low temperature. Copper will never be a superconductor or isn't a superconductor. And you might say, well, why then don't we use these? Well, think about this. We do bury cables underground, and the reason why we go underground is because it is cooler. Okay, but think of this: to maintain a wire at -200 and say 50 degrees Celsius, again, you're going to be putting more energy into it to create that cold temperature than is going to be economically efficient, okay, or beneficial to you. So that's the reason why we still continue to go with copper. Electrical safety. You know that if you're taking a shower or a bath to keep electronics away, if you jump out of the pool, again, stay away from electricity. And let's go ahead and let's examine that. Okay, so the why is, okay, as you're sitting here maybe watching this video, I'm thinking you probably didn't come in from working out, but dry skin alone has a resistance of 500,000 ohms. Okay, lots of resistance. Well, if we have lots of resistance, that means that we're going to have very little current. So if you have dry skin and you accidentally, say, touch an outlet and get shocked, you're going to experience a current of 0.00024 amps. And what it is anything less than 0.001, you might get that slight shock, you might get that slight tingle, things like that. So again, high resistance, low current. Well, I hope you made that connection earlier, but when resistance goes up, current goes down. Okay, but let's examine working out. Let's examine getting out of a pool. Let's examine taking, the shower or bath. If you have wet skin, your resistance drops to about 100 ohms. So notice we went from 500,000 to 100. So resistance went way down. Because they are indirectly related, you're going to notice that current's going to jump up. So when that current jumps up, it might jump up to about 1.2 amps. If we use that 100 ohms, jumps to about 1.2 amps. Anything greater than 0.15 amps can be fatal to the body, basically disrupting that normal heartbeat that you have. Okay, so a little bit talking about electrical safety, some of the relationships between voltage, current, and resistance.